Okay, welcome back, my dear students. ഞാൻ മുൻപ് ഗ്യാസ് സ്റ്റേറ്റിൻ്റെ പാർട്ട് 1 വീഡിയോ നിങ്ങൾക്ക് അയച്ചു തന്നിരുന്നു. കുറച്ച് മുൻപാണ്. അതിനുശേഷം നമ്മൾ പിന്നെ സോളിഡ് സ്റ്റേറ്റാണ് ഡിസ്കസ് ചെയ്ത്. സോളിഡ് സ്റ്റേറ്റ് ഓവർ. ഇനി ഗ്യാസ് സ്റ്റേറ്റിലെ പാർട്ട് 2 ആണ്. ഇത് അതിൻ്റെ അവസാനത്തെ വീഡിയോ ആണ്. ഇതിൽ നമ്മൾ ഡിസ്കസ് ചെയ്യുന്നത് ബിഹേവിയർ ഓഫ് റിയൽ ഗ്യാസസ് എന്ന് പറയുന്ന പോർഷനാണ്. ബിഹേവിയർ ഓഫ് റിയൽ ഗ്യാസസ്. അതായത് ഐഡിയൽ ഗ്യാസ് ഇക്വേഷൻ നമുക്കറിയാം അല്ലേ? ഐഡിയൽ ഗ്യാസ് ഇക്വേഷൻ ഒക്കെ നമ്മൾ മുമ്പ് പഠിച്ചിട്ടുണ്ട്. ദാറ്റ് ഈസ് പി വി ഇസ് ഈക്വൽ ടു NRT. ആ ഐഡിയൽ ഗ്യാസ് ഇക്വേഷൻ ഒബേ ചെയ്യുന്ന ഗ്യാസുകളെ നമ്മൾ എന്ത് വിളിക്കുക? ഐഡിയൽ ഗ്യാസ് എന്ന് വിളിക്കുക. ഐഡിയൽ ഗ്യാസ്. ബട്ട് നൺ ഓഫ് ദ ഗ്യാസ് ഈസ് പ്രാക്ടിക്കലി ഐഡിയൽ or no gas is completely ideal. That is, it does not obey ideal gas equation at all temperature and pressure. Normally all gases deviate from ideal behavior. Okay, and that gases normally the gases are real gases, not ideal gas, because they do not obey ideal gas equation do not obey ideal gas equation at all temperature and pressure. That is real gases. Okay, can you follow me? Okay, real gas is the gases which do not obey ideal gas equation at all temperature and pressure. Normally all gases are real. They do not obey ideal gas equation completely. Okay, and they obey ideal gas equation. Real gases obey ideal gas equation. Real gases also obey ideal gas equation only at high temperature and low pressure. Okay, that is, real gases become ideal or shows ideal behavior at low pressure and high temperature. Okay, at all other conditions they deviate from ideal behavior. Okay, real gases shows ideal behavior. Real gases shows ideal behavior at low pressure and high temperature. Okay, and all other conditions they deviate from ideal behavior. And under normal conditions of temperature and pressure, they show deviation from ideal behavior. They deviate from ideal behavior. And these deviations are high at low temperature and high pressure. Low temperature and high pressure, they deviate from ideal behavior. Okay, and then ഈ ഡീവിയേഷന്റെ എക്സ്റ്റെൻഡ് കണ്ടുപിടിക്കാൻ വേണ്ടി നമ്മൾ ഉപയോഗിക്കുന്ന ഒരു ടേമാണ് കംപ്രസിബിലിറ്റി ഫാക്ടർ, സെഡ്. നമ്മൾ അതിനെ സെഡ് എന്ന് ഡിനോട്ട് ചെയ്യുക, കംപ്രസിബിലിറ്റി ഫാക്ടർ. അതായത് നമുക്കറിയാം പി വി ഈസ് ഈക്വൽ ടു NRT ആണല്ലോ. അപ്പൊ അങ്ങനെയാണെങ്കിൽ പി വി ഡിവൈഡഡ് ബൈ NRT ഈസ് ഈക്വൽ ടു 1 അല്ലേ വരണ്ട്, ഐഡിയൽ ഗ്യാസ് ഇക്വേഷൻ ഫോളോ ചെയ്യുകയാണെങ്കിൽ. പക്ഷെ ഇൻ ദ കേസ് ഓഫ് റിയൽ ഗ്യാസസ് ഇറ്റ് ഈസ് നോട്ട് ഈക്വൽ ടു 1 ആൻഡ് ദിസ് ടേം ഈസ് ഡിനോട്ടഡ് ആസ് സെഡ്. ആക്ച്വലി ദിസ് ഈസ് കംപ്രസിബിലിറ്റി ഫാക്ടർ, ദാറ്റ് ഈസ് Z ഈസ് ഈക്വൽ ടു പി വി ഡിവൈഡഡ് ബൈ NRT, or V by N is the molar volume, so we can write PVM divided by RT for 1 mole of gas. For 1 mole of gas we can write Z is equal to PV by RT, compressibility factor. Okay, normally Z is equal to 1 for ideal gas. For ideal gas Z is equal to 1, and for real gases it is not equal to 1, and greater the deviation departure set from unity, more the deviation from ideal behavior. Okay, when Z value depart from the unit value, that means it shows more deviation from ideal behavior. That means compressibility factor is a measure of deviation from ideal behavior, ideality. Okay, Z less than 1 implies gases is more compressible. Okay, that is when Z is less than 1, that is Z is actually is equal to PV divided by, or we can say in another term PV observed divided by PV ideal. That is another expression for Z. Okay, Z less than 1 means Z less than 1 means the observed value of PV is less. Observed value of PV is less. That means the gas is more compressible. When Z greater than 1 means gas is less compressible. When Z greater than 1 means the observed value of PV divided by PV ideal. When Z greater than 1 means observed value of PV is higher. That means it is less compressible. And Z is equal to 1 for the ideal gas. For ideal gas, Z is equal to 1. ഓക്കെ, ഈ ഡീവിയേഷൻ്റെ ഒരു പ്രോപ്പർട്ടി അല്ലെങ്കിൽ ഡീവിയേഷൻ്റെ ഒരു നാച്ചർ മനസ്സിലാക്കാൻ വേണ്ടി നമ്മൾ ഒരു ഗ്രാഫ് പ്ലോട്ട് ചെയ്യാണ്. ഇവിടെ നമ്മൾ പ്ലോട്ട് ചെയ്യുന്നത് സെഡ് അഗൻസ്റ്റ് പി. ഓക്കെ, കംപ്രസിബിലിറ്റി ഫാക്ടർ അഗൻസ്റ്റ് പ്രഷർ പ്ലോട്ട് ചെയ്യാണ്. അപ്പം അങ്ങനെ പ്ലോട്ട് ചെയ്യുമ്പോൾ നമ്മൾ സാധാരണ കാണും, നോർമലി in most of the gases, Z first decreases with increase in pressure. Okay, for all normally for all gases, Z first decreases and reaches a minimum value and then increases. This is a graph for carbon dioxide. And for CH4 also, the Z first decreases with increase in pressure and then increases. And this is for nitrogen, first decreases and then increases. And the extent of deviation is different for different gases. Okay, and that is a normal behavior of gases. But in the case of hydrogen and helium, this is the graph for hydrogen. Z always increases, no decrease, always increases with increase in pressure at 0 degrees Celsius. This graph is plotted at 0 degree. At 0 degree for hydrogen, Z increases, and for helium, this is graph for helium. These two are, this is for the hydrogen, this is for helium. For these two gases, Z always increases. And for all other gases, Z first decreases, that is less than 1, and then reaches a minimum value, then increases. Okay, that is a normal behavior of gases. But in the case of hydrogen and helium, this is for helium and this is for hydrogen, Z always increases. Okay. ഓക്കെ, അപ്പോൾ ആ ഗ്രാഫ് എന്ന് മനസ്സിലാവുന്ന കാര്യം ഇവിടെ നമ്മൾ കൺക്ലൂഡ് ചെയ്യാം. അറ്റ് വെരി ലോ പ്രഷർ Z is equal to 1 for all gases. Okay, that I didn't tell you. Look at the again that graph. Okay, you can see that at almost at about this pressure, that is at about 10 atm, that is at very low pressure, Z is equal to 1 for all gases. Okay, that means at very low pressure, all gases obeys ideal gas equation. Okay, that is the first point. At very low pressure, Z is equal to 1 for all gases. That is, all gases behave ideally at very low pressure. And for gases like nitrogen, oxygen, carbon dioxide, etc., Z first decreases. That is, it is more compressible and pass through a minimum, then increases continuously and eventually becomes greater than 1. That we have observed in the graph itself. And for hydrogen and helium, Z continuously increases with increase in pressure at 0 degrees Celsius. Okay, for in the case of hydrogen and helium also, the graph become like this. Okay, that's first decrease increases, but at a temperature of minus 165 degree for hydrogen, at below temperature of minus 165 and below a temperature of minus 240 for helium, the graph also, in the case of hydrogen and helium also, graph behave like this. And above this temperature, graph will be like this for hydrogen and helium. Okay, that is this type of graph we get for hydrogen and helium because we plot the graph at 0 degree. If we plot the graph for below minus 160 for hydrogen, graph will be like this. And below minus 240 for helium, the graph will be like this. Okay. Then, in another graph, we are discussing another graph. This is Z versus P. Again, Z versus, this is compressibility factor Z against pressure. We are plotting Z against P. For a particular gas, we are plotting for a particular gas at different temperature. In the first graph, we are plotted different gases at a particular temperature. Okay, and here it a particular gas at different temperature. You can observe this is a graph for or nitrogen. For nitrogen we are plotting, and this is at this blue line is at minus 220 Kelvin. We can see that Z first decreases and then increases. Okay, and this blue line I will draw with blue. Okay, and this green line is at minus 273, that is temperature increases. Then you can see that the deviation minimizes, that is this depression in Z decreases, only a small depression and then increases. That is deviation from ideal behavior is less when temperature increases. And this graph, that is this yellow line is at 327 Kelvin, approximately 50 degrees Celsius. The graph is almost ideal behavior. Okay, at about this pressure, that is about 125 pressure, 125 atm pressure, the nitrogen shows ideal behavior. That means at this temperature, nitrogen behave almost ideally at an appreciable range of pressures, and that temperature is called a boil temperature, or it is called a boil point, 50 degrees Celsius for nitrogen. And above that temperature, we can see that above that temperature Z increases. No dip in the curve, always increases. Below 50 degrees Celsius, nitrogen first decreases and then increases. When temperature is further lower, the dip first also increases. Okay, that means when temperature increases, deviation from ideal behavior decreases, and at a particular temperature, for all gas there is a particular temperature. For nitrogen it is 50 degree. Okay, different gases, different boil temperature. At that temperature, all gases behave ideally, because the reason for that is that at that temperature, the interaction between the molecule, that is attractive force between the molecule and repulsive force, cancel each other, and that is a particular temperature that is different for different gases, and that is called the boil temperature. Okay, we can summarize the discussion, that is dip in the curve is greater at low temperature. When temperature is become more lower, the dip in the curve is greater. The dip in the curve decreases with increase in temperature. We can see that when first like this, when temperature increases, the dip in the curve decreases. Okay, and at a particular temperature, 50 degrees Celsius for nitrogen, the minimum in the curve vanishes, and the curve remains almost horizontal. That is for nitrogen, for at 50 degrees Celsius, the curve is almost like this, and above 50 become less, and below 50 like this. Okay, and Z is approximately equal to, for an appreciable range of pressure, and below Boyle's law is obeyed. This temperature is called Boyle's temperature because at this temperature Boyle's law is obeyed, and so it is called Boyle point. So Boyle temperature is the Boyle temperature is the temperature at which gases obeys Boyle's law at an appreciable range of pressures. That is Boyle temperature. Boyle temperature is the temperature at which gases obeys Boyle's law or ideal gas equation. Obeys Boyle's law, or we can say ideal gas equation, over an appreciable range of pressures. Okay, then what is the causes for this deviation? Okay, why real gases deviate from ideal behavior? Actually, the theoretical base for ideal gas equation PV is equal to nRT is actually kinetic theory. Okay, we have studied kinetic theory in the last first video. Okay, that is kinetic theory is the basis for the ideal gas equation. Ideal gas equation is actually derived from various gas laws, Boyle's law, Charles' law, and Avogadro's law, and later it is theoretically proved by kinetic theory. Okay, so the deviation from ideal behavior, the reason for deviation is deviation from ideal behavior also due to the kinetic theory. Actually, the two faulty assumptions of kinetic theory is the reason for deviation from ideal behavior. The first one is we have a postulate that the volume of the gas molecule itself is negligible. Okay, compared to the total volume of the gas, suppose this is the total volume. This is the total volume. Then molecules are occupied in this. If these molecules are combined together, then there is a smaller volume like this. If we place all the molecule in a packed manner, there is a small volume, and this volume is negligible according to kinetic theory. But it is not true at high pressure and low temperature. This is true at very low pressure and high temperature, because at very low pressure, high temperature, the overall volume will be high. There is a larger volume of the gas. Then in that volume, the volume of the gas molecule itself is negligible. But in all other conditions, that is at normal temperature and pressure, this postulate is not true. That is, volume of the gas molecule itself is not negligible. There is a considerable volume for gaseous molecules. Okay, and another postulate is there is no force of attraction between the molecule. Okay, there was a postulate in kinetic theory, that is, there is no attractive force between gas molecule. This is also true only at very low pressure and high temperature, at which the volume of the gas molecule is high. When pressure increases and temperature decreases, volume of the gas molecule decreases. Okay, then compared to this small volume, the molecules will be close to each other. Then there will be a considerable attractive force between gas molecule. Okay, so these two postulates are correct at low pressure and a high temperature, but all other conditions, these two postulates are wrong. That is the reason for the deviation from ideal behavior. Okay, അപ്പോൾ ideal gas equation നോർമലി ഗ്യാസുകൾ ഒബേ ചെയ്യാത്തതുകൊണ്ട്, റിയൽ ഗ്യാസ് ഒബേ ചെയ്യാത്തതുകൊണ്ട്, റിയൽ ഗ്യാസിന് കൂടി അപ്ലിക്കബിൾ ആകുന്ന രീതിയിൽ ഐഡിയൽ ഗ്യാസ് ഇക്വേഷനെ കറക്റ്റ് ചെയ്തുണ്ടാക്കിയ കുറെ ഇക്വേഷൻസ് ഉണ്ട്. അതിലൊരു പ്രധാനപ്പെട്ട ഇക്വേഷൻ ആണ് വാണ്ടർ വാൾസ് ഇക്വേഷൻ ഓഫ് സ്റ്റേറ്റ്, വാണ്ടർ വാൾസ് ഇക്വേഷൻ. ഓക്കെ, വാണ്ടർ വാൾ എന്താ ചെയ്യുന്നത് വെച്ചാൽ he introduced two correction terms in the equation PV is equal to nRT. Correction term for volume and correction term for intermolecular force of attraction. ഇതിന്റെ ഡെറിവേഷൻ നമുക്ക് ആവശ്യമില്ല, കോംപ്ലിമെന്ററി കോഴ്സിന് ഡെറിവേഷൻ is not needed. So directly we can go to the equation. This equation is P plus an square by v square into v minus nb is equal to nRT. Okay, P plus an square by v square into v minus nb is equal to nRT for n mole of gas, and for 1 mole we can write P plus a by v square into v minus b is equal to RT for 1 mole of gas. And this a and b are called van der Waals constants. Okay, a and b are called van der Waals. Okay, significance of a and b. The van der Waals constant a is actually introduced due to the intermolecular force of attraction. So a is a measure of intermolecular force. Okay, higher the value of a means there is stronger intermolecular force of attraction, so that gases are easily liquefiable. Okay, clear? For example, if you consider HCl and oxygen, HCl is polar, O2 is non-polar, so intermolecular force of attraction is higher in HCl. Therefore, value of A is greater in HCl than in O2. Okay, so intermolecular force of attraction is measured by A, or A is a measure of intermolecular force of attraction. So higher value of A means stronger intermolecular force of attraction. That means that gas is easily liquefiable. And van der Waals constant B, actually it is proportional to size of the molecule. Okay, it is because van der Waals constant B is introduced due to the volume of the gas molecule, considering the volume of gas molecule, so it is proportional size of molecule. It is actually 4 times the actual volume of gas. B is not the actual volume, B is not the actual volume of the gas, it is actually 4 times the actual volume of the gas. Okay, this much is needed for your complementary course. Our chapter is over. Okay, thank you.